we look at the third page of this talk about congruent triangles and corresponding parts and attributes of triangles, a good question, a good set of questions here is, which postulate could you use to say that these triangles are congruent? You got to name the triangles carefully, and you got to tell me which postulate was used. And oh goodness, I'm gonna have to put some letters over here when I'm going to call this place P and this place Q, just so I can talk about it. That needed to be already in place. And it tells me triangle SAT is congruent with, is there another triangle here? Congruent with that one? What we'd have to think right away is, yeah, those right angles are congruent to each other. Not only that, but those vertical angles are congruent with each other as well. Little deduction there. And then I got two angles and a side congruent to two angles and a side. So I'm thinking we do have congruent triangles. And if I call this one SAT, the congruent triangle partner with that one would have been, I think S matches with Q, QPT. And I got to talk about what postulate I used. And this one would have been angle, angle, side matching angle, angle, side. Perfectly valid postulate, angle, angle, side. Guarantees that these triangles are congruent. That'd make angle S congruent to angle Q by corresponding parts. But that's just not what I care about right now. Look here. Apparently this is an isosceles triangle. It's marked that way. And we got an angle bisector, don't we? I look at these two triangles. I wonder if triangle PAT is congruent to the other guy. And I realize AT is congruent to itself. These are the kind of little decisions you'd want to make by the reflexive property. And that would guarantee congruent triangles, wouldn't it? Let's name them with care. Triangle PAT congruent to triangle ZAT. How'd you get it to be congruent, mister? What postulate did you use? This would have been side, angle, side, matches side, angle, side. That fits, doesn't it? I like this one too. Got a couple of congruent sides. PO is congruent with ZC, but they're also parallel. Now, if those lines are parallel, wouldn't you have some congruent angles? I'd go around looking for alternate interior angles and mark them to be congruent. I believe that this angle at P would be congruent to this angle at C. Those are alternate interior angles. I also see that the reflexive property applies here. So I got enough stuff going on here to say that these triangles are congruent. If I call this one POC, the angle at P matched the angle at C, so I'd have to start with C there. POC would match CZP, I think. I can check on that. Is PO congruent to CZ, and PO is congruent to ZC. So yeah, I'm happy. I think I've named those correctly. And what postulate have I met, if I've met one at all? I got a side, an angle, and a side congruent to a side, an angle, and a side. So let's look again. Here's a kind of an interesting case right here. Got a couple of triangles. And this is a right triangle. I know that this right angle is congruent to this right angle. And this, the hypotenuse of this one is congruent to the hypotenuse of that one, already marked that way. And I know that DG is congruent to itself. I'll put a lot of marks on that one, like the reflexive property shows. And I wonder if I got congruent triangles or not. I got an angle, a side, and a side congruent to an angle, a side, and a side. Hey, maybe these are congruent by angle, side, side. For some reason your teacher never did talk about angle, side, side. Maybe he's embarrassed to write angle, side, side like that. Maybe he just he's scared to talk about it. Actually, that's not the problem. Let me show you here. Here's a couple of triangles. And I say that the angle at P is congruent to the angle at A. And I did show AB congruent to PQ, and those are the same length. These angles are the same measure. And this length BC is as big as this length QR. Hey, an angle of side to side matches an angle of side to side. Are these triangles congruent by angle side side? I was like, no, man. Angle side side is not a valid postulate. It's not because I'm embarrassed to write it. It just does not give congruent triangles. So when I go back here, I got to say, I don't think any triangles are necessarily congruent here. I have not met a postulate that is valid. I don't really need to talk about that much more, but no, I don't have any congruent triangles there. Something to be thoughtful about. But you'll remember, and I got 4 postulates to care about. Side, angle, side's important. Angle, side, angle's important. Side, side, side. And angle, angle, side. Looking for those postulates. Here I'm going to show a part of a proof. And you got to tell me what reasons were going on. You turn off this video and think about it ahead of time, but I'm going to walk you right through it. Apparently, this is the given, wouldn't it be? I'm going to have to mark it that way. AD is parallel to BC. And AD is congruent. I got a single pair of signs that are parallel and congruent. That would be the given, wouldn't it? That's always going to be true. The first step will always be given. It says show DB. I have to do that right away. You'll be thinking about what makes you think you have the power to show DB. D was there and B was there. You figure DB would exist? I think so too. I say for every 2 points, there exists a line. I want to show a part of that line. I show DB. Then it starts talking about angles. And since we do have these parallel lines, I think we may have some angles to think about. Angle ADB, that's this one, is to be congruent with angle CBD, this one. Any reason to think those angles would be congruent? They're not vertical angles, are they? No, that's not what's happening. Yeah, but if these are parallel lines, wouldn't those angles have to be congruent? Yeah, these are congruent angles because parallel, then alternate interior angles would be congruent. That's kind of a scribbled message right there. Let me say it clearly. If lines are parallel, then we have alternate interior angles congruent, and I'm saying that these are alternate interior angles. Now, it tells me this bold statement that DB is congruent to itself. I don't make those kind of marks. DB is congruent to itself, and there's got to be a good reason for that. You say, well, any single thing is congruent to itself, but we got a name for that property. We're going to call that the reflexive property. And then talks about congruent triangles. And pretty much every proof we're ever going to do is going to get a couple of congruent triangles and then talk about their corresponding parts. Why would these triangles be congruent? And it should be obvious from looking at the marks that have been made here. We've got a side, an angle, and a side congruent to a side, an angle, and a side. Yeah, those are congruent triangles by side, angle, side. And very typically, once you got congruent triangles, you're going to look at some parts. Is it true that angle DBA matches with angle BDC? Yeah, I'm thinking those would be congruent angles. Let me look at them in this picture. Angle DBA, this angle, congruent with angle BDC, that one. Yeah, those would be congruent angles, and corresponding parts of congruent triangles are congruent. So I concur that those angles must in fact be congruent. And what about this? How in blazes are we going to get AB, this segment, to be parallel to that one? These angles that we just talked about have any relationship with those lines being parallel? I say yes, they do. As a matter of fact, it's the converse of this theorem. This thing tells me if lines are parallel, then we got congruent alternate interior angles. That's really a biconditional. If you got congruent alternate interior angles, then these lines would have to be parallel. So I'm going to state the converse of this. Congruent alternate interior angles, like showed right here, then parallel lines. And that would be a good little way to solve that proof. Now, just in the way of practice, this is probably what's going to happen. What happened on this test was they only had to do one of these two proofs. I think I'm going to ask you to do more than that, but I'm going to tell you about those proofs ahead of time. I've got these sketched on another page. I'm going to pull up that other page and go to work with it here. You'd want to get that sketch and think about this proof yourself before I do it. But I'm ready to jump right in and go. It tells me WV is perpendicular to WY. Just ahead of time, I'm going to make a right angle there. And ZY is also perpendicular to WY. All right. So I got a couple of right angles, and right angles are always congruent to each other. I know that'll be important. It also tells me that WV, this segment, is congruent to ZY, that one. I'm just thinking to myself ahead of time, I'm thinking that these vertical angles are going to be congruent. And so I'm going to be wondering, have I met a postulate there with those ideas? I know I haven't done any writing yet, but Just looking ahead. I got the given in place, and if you say, man, I have a hard time with proofs, I'll just say, investigate that given. It gives you lots of ideas to think about. And let's go to statement 2. So, is angle W congruent to angle Y? We're going around thinking they are. They're both right angles. I'd say yes, they are. They are congruent. Angle W is congruent with angle Y because all right angles are congruent. That's why I think that those are congruent angles. And I ought to mark them that way. They were really kind of marked that way when I showed them both to be right angles, but let's clue it this way. Then we had other angles to talk about too, didn't we? I know these sides were congruent, that was given. But these vertical angles are congruent. Let's make a note about that. And I'm going to call it angle WXV is congruent with its vertical angle partner, YXZ. I know that those are congruent because vertical angles are always congruent. Vertical angles congruent. Therefore, have you got congruent triangles here, mister? Well, let's take a look. Have we made a postulate here? I'm thinking that we have. You think about that postulate. Let's make a note about the congruent triangles. I'll call the first one triangle. WXV is congruent with triangle. Got to name the second with care, and I start with the right angle. I'll start with the right angle there. Y, WXV, YXZ. And how in blaze did you get those triangles to be congruent? Yeah, that was side. No, that's not side. I could call it side angle, but it's truly angle, angle, side, congruent to angle, angle, side. So I got congruent triangles, which is the main thing. Yeah, once I got the congruent triangles, there should be some kind of way I could come up to this conclusion. Let's go in that direction. What would make you think that X is the midpoint of VZ? What would make you think that X is the midpoint of VZ? If Vx was congruent to XZ, I'd be thinking, yeah, that must be a midpoint, huh? And I think that would have to be true that Vx is congruent to XZ because they're corresponding parts of these congruent triangles. Let's put that on paper. Vx, you're congruent to XZ. Must be true because corresponding parts of congruent triangles are congruent. And just about to finish this little proof up. If I know that Vx is congruent to XZ, would X have to be the midpoint? Well, yes, it would. It's doing what a midpoint's supposed to do. It must in fact be one. I don't want to write that right there. I gotta think of something more clever than that to write, but I'll say X is the midpoint of segment VZ. I gotta talk about why I thought so here. Just because it divided this segment into 2 equal parts, you think it's a midpoint. I say, yes, I do. Definition, midpoint. It acts just like a midpoint. It must be one. And that's a quick little proof right there. I like that one. I think that's a good one. I want you to be able to know about midpoints and vertical angles and put those together. I'd study that one. Let's look at this guy too. Triangle ADC is isosceles with base AC. And DB is an angle bisector, it tells me. I'm supposed to prove that DB is perpendicular to AC. Let's make some marks here ahead of time from this given. If ADC is isosceles with base AC, these must be the legs. I'm just thinking ahead of time. I'm going to have to write about that in a moment. But it also tells me that DB bisects angle ADC. That makes me think that these angles would have to be congruent, wouldn't they? Because if you've got an angle bisector, it's going to divide the angle into 2 congruent parts. And yeah, I'm going to get congruent triangles here some kind of way. I'm always going to work on trying to get congruent triangles, and we're going to have to figure a way to get lines to be perpendicular in a moment. You might have a method about that. I know we've done a proof about it before, but we've done a few proofs, and it's hard to keep everything straight. Let's see if we can't get the triangles to be congruent first. I go to the second step. I've got my given in place. So what is isosceles? So what does that tell you? Well, we got to have a couple of congruent sides. I'd say right off the bat, AD is congruent with CD. Just because it's isosceles, you think you got to have a couple of congruent sides. I say, yes, I do. Definition, isosceles triangle. And if we have this angle bisector, DB bisects angle ADC, wouldn't those angles be congruent? I might put a 1 and a 2 in there so we can talk about it quickly and easily. Angle 1 is congruent with angle 2. Just because you got an angle bisector, you think those angles would be congruent? And I say, oh, I do. Because the definition of an angle bisector, that's what angle bisectors are supposed to do. How are we going to get these triangles to be congruent? Do I need another segment or something? Yeah, I do, don't I? DB is congruent to itself. Cheap and easy, be aware of the reflexive property. DB congruent to itself by virtue of the reflexive property of congruence. And then, have we got congruent triangles? I believe we do. Let's make a note about it. Triangle, I'll call mine ABD, is congruent with, and its partner would have to be named ABD is going to match with CBD, huh? And what was the reason for our statement 5? What makes you think those triangles are congruent? Is it angle side side? I don't think so. This was side angle side matching side angle side, huh? The most common of the postulates, I'm pretty sure. Now, about half the battle, a little more than half, is getting these triangles to be congruent. We've got to find a way to make DB be perpendicular to AC. We're going to want to talk about these couple of angles, huh? And truthfully, if DB is perpendicular to AC, what we got to do to make them be perpendicular is say that these are right angles. I have proven with you before, and we're just going to touch some bases here, that if two angles are congruent, equal in measure, and add up to 180, they're going to have to be 90 each, aren't they? If two angles are congruent and supplementary, then they are right angles. I got to think, are these two angles congruent? I say, yeah, they are, man. They would have to be. Angle 3 is congruent with angle 4. Why do you think so? Well, they're corresponding parts of these congruent triangles. That's why I think so. You're almost always going to get congruent triangles and talk about some parts, and then put those parts to work to make it be a midpoint or make it be perpendicular or whatever you got to do. So, angle 3 is congruent with angle 4. I know that they're equal in measure, but do they add up to 180? Yes, they must. How makes you so sure? Well, I'm going to say, I can say it this way. Angle 3 and angle 4 are a linear pair. What makes you, I think I probably should have said they're supplementary. Let me say that angle 3 and angle 4 are supplementary. What makes you think they're supplementary, mister? Well, if they're a linear pair, they got to be supplementary. That's called a linear pair postulate, as a matter of fact. So here I say that angle 2, 3, and 4 are supplementary. But then they can finish this proof right here, right now. These angles are congruent and they're supplementary. So if they add up to 180 and they're as big as each other, don't they got to be 90? And I think we can say quickly and easily on the 8th step right here, angle 3 and angle 4 are right angles. Why, Mr. Why? And you say, well, I'll tell you why. Two angles, congruent and supplementary, implies right angles. Pretty much done with this proof, but I think we could touch one more statement on here. So what, these are right angles? Okay, you got them being right angles, huh? Does that make them be perpendicular? Does that make DB perpendicular to AC? Under what circumstances are lines perpendicular anyway? And you'd say to yourself, well, lines are perpendicular if and only if they form right angles. These form right angles, so they're perpendicular. I can conclude this proof. DB is perpendicular with AC. What makes you so all fired sure that's true, mister? Well,